All right, students, we're going to start going through our packet. I am going to start us on page 2 of the packet, not page 1, just to make things go a little quicker. The periodic table I'm using does look like it might be a little hard to read on the video, but I will be going slowly and pointing to things all along. So let's start with neon. Neon, its atomic number is 10. That means it has 10 protons. So atomic number 10, 10 protons. And if we are talking Ne, ooh, that's a horrible pen. Let me use this one. Ne with 0 charge. That means it has 10 negative electrons, canceling 10 positive protons. We don't write those positives and negatives when we're just reporting the number of electrons, but I'm writing it there to show that 10 positives balances 10 negatives to give you 0 charge. Now the group number is 8A. 8A. You could also write 18. You could also write 18 because as we go right to left, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 18. Valence electrons. If you're using classic group nomenclature, this thing, it's 8. 8 valence electrons. You can't get the valence electrons from this number, but you can get it from the Roman numeral group numbers. Lewis dot structure for Ne. Remember, we do 1, 2, 3, 4, and then start pairing 1, 2, 3, 4. It's 8 total valence electrons in the Lewis dot structure. Because this is a noble gas, these are the noble gases, they do not react very easily at all. So in order to become electrically stable, they don't need to gain or lose electrons because they're already electrically stable with 8 valence electrons, or the exception 2 for helium. So the answer is does not gain or lose electrons. Does not gain or lose electrons. And the charge of this would be 0. 0 charge. Does not ionize. Does not ionize. So again, hopefully this is coming out okay on the camera. Might be able to zoom in a little bit better. Let's jump to sodium. Sodium is Na. And again, we're talking with 0 charge at the moment. The atomic number is 11. Na is 11. Remember, sodium, it's a symbol comes from that Latin word naturum, I believe. Could be wrong about the pronunciation of that. But either way, its atomic number is 11, which means 11 positive protons. You don't need to write the positives. But for these purposes, it's not bad to write them out. If we have 0 charge, 11 positives are canceled by 11 negatives. And we are in group 1A, which means we have 1 valence electron. So group 1A means we have 1 valence electron. Na gets 1 dot. Now, Na can have 2 options to form an ion. It can gain 1, 2, 3, 4, 5, 6, 7 electrons, giving it a -7 charge, or it can lose 1 electron to become electrically stable like neon. It's going to lose 1 electron and not gain 7 because of the amount of proton pull that it has to become electrically stable. Works out more energetically favorable to just lose the 1 electron. So when it does form an ion, it becomes Na 1 positive. And that means it loses one electron. Okay. The charge of that ion is again Na1 positive. We'll get into later if we write one positive or positive ones. For now, there should be no difference in your mind. Magnesium, Mg. Let's start with uncharged. It's number 12, which has 12 protons, 12 electrons. And because it's right here in group 2A, it's got 2 valence electrons, Mg, 1, 2. If you're, it really does not matter. Never mind. I'm not going to say that. If you want to draw the dot here, that's fine. There's arguments for putting these 2 electrons together here, which I actually favor that, but let's just be consistent with how we do things. So now we are going to have Mg. It's going to lose these 2 electrons, which is going to make it 2 positive. Remember, if you lose negativity, you leave positivity behind. So we're going to lose 2 negative electrons, and that's going to give us Mg 2 positive. Now, I'm going to jump down to sulfur. And the reason I'm going to jump down to sulfur, let's see, can I get that on this paper in a wise way in the camera view? No, I cannot, but I can get phosphorus in there, and that's going to show the same principles. So let's do phosphorus P. All right, phosphorus P is right here in group 5A. It's got 15 protons, which means its atomic number is 15, 15 protons, and if we're uncharged, 15 negative electrons. We said it's in group 5A, which means it has 5 valence electrons. And P will have 1, 2, 3, 4, 5 dots. That's how we're teaching that Lewis dot structure. And we're going to gain to get to 8 outer electrons, 1, 2, 3. It's going to gain 3 negatives. It's got enough protons to pull in 3 negatives to become stable like argon. And the amount of protons it has, it's not energetically favorable for it to lose 1, 2, 3, 4, 5. It's more energetically favorable for it to become stable by gaining 3 electrons than losing 5. Okay, so the number of electrons gained or lost is going to be gains 3. Gains 3. I would actually like, it'd be nice to have you guys do an exercise where you consistently say it gains 3 electrons to become electrically stable like argon, or oxygen gains 2 electrons to become electrically stable like neon, or beryllium loses 2 electrons to become electrically stable like helium. That would be a good exercise to do. Maybe we'll do that soon. All right, so our charge on the ion is going to be P3 negative. By gaining those 3, it's going to get 1, 2, 3, 4, 5, 6, 7, 8 dots around it. Okay, that's enough intro for that page. Let's move on to putting together ions and ionic compounds. Let's move on to this one. So the first thing I'm going to do with this is show you guys the symbols for all of these for time purposes. So sodium is Na. I'm going to write the group number up here too. Group numbers. And the reason I'm going to write the group numbers is that's going to help you with knowing the valence electrons. So sodium is right here in 1A again. So 1A. Fluoride is F. That's over here in 7A, 7A. And because we know those group numbers match to valence electrons, sodium has 1 dot, fluorine has 7 from group 7A. Fluorine 1, 2, 3, 4, 5, 6, 7. I'm going to pair that one up there because I want to show this one moseying on over into that pocket right there. So now by doing that, we have Na positive, we have F negative, and those two come together to make NaF. Now you don't need to draw the dots here because it's a complete shell. But since we're showing that this one lost an electron, leaving a positive behind, it might make a little sense to show those dots here. So where fluorine had 7 valence electrons, now it has 1 extra, giving it overall a -1 charge. All right, moving on. Lithium sulfide. Lithium is in group 1A. 1A. Sulfide. Sulfur is in group 6A. And that's going to be S. I'm not drawing the dots here, so let's just get rid of that. All right. So lithium, it's in group 1A. It's got 1 valence electron. Sulfur, S, it's in group 6A, so it's got 1, 2, 3, 4, 5, 6. Now, I'm leaving these two unpaired for a reason. This lithium is going to donate that 1 electron right there. But there's a problem. When it does that, sulfur is still missing, even though it got that extra electron from lithium, it'll only have 7 around it if it gets that. So we're going to need another lithium to donate the 8th electron for sodium. By doing that, we now have 2 lithiums. So if you were to show these two things reacting, later on, we're going to show a way that designates or shows how there are 2 lithiums here. But for the time being, we know lithium lost 1 electron, which makes it positive. And sulfur has gained 2 negative electrons, so it's a 2 negative, making it Li. S. How many lithiums do we have? 2. Li2S. Let's keep going. Looking for calcium, which is Ca, and bromide, which is Br. Ca is right here, and Br is right here. Br is in group 7. So I'm going to go ahead and write that. It's in group 7. And calcium is in group 2. 2A, I should say, and 7A. And because of that, let's go ahead and write the valence electrons. Ca, 1, 2, and Br, 1, 2, 3, 4, 5, 6, 7. Now, we have a similar situation to the last problem where we make these dots a little bit bigger for the video. The calcium is going to donate 1 electron to bromine. And the problem is it has not achieved getting rid of its valence electrons to go back 1 shell. Calcium wants to lose 1, 2 electrons to become electrically stable like argon. However, it still has this valence electron. So we're actually going to need another bromine. So I'm going to go ahead and write 1 more bromine right here. I'm going to go 1, 2, 3, 4, 5, 6, 7. So now I have this other bromine here, and this electron is going to go to that bromine. And by doing that, bromine gets 8, this bromine gets 8, And calcium gets 8 electrons in its shell right beneath this one. So remember, we have a valence shell here. And underneath that are more electrons. Argon, right underneath, has 1, 2, 3, 4, 5, 6, 7, 8 electrons. If we get rid of these 2 valence electrons, now we have a nice, happy, stable outer shell with 8 that got revealed underneath. So anyway, calcium lost 2, so it's 2 positive. And bromine gained 1, so it's 1 negative. And that gives us CaBr2, because there are 2 bromines required for this to happen. All right, see, strontium iodide is Sr. That's going to be right here in group 2. So again, 2A. And iodide is I'm writing group numbers. That's in group 7A. See, I think that's very similar to the last problem. So I'm going to go ahead and skip that one in the video just to keep things short. Potassium, that's K. Potassium's right here, K. That's going to be group 1A. And oxide is group 6A. That's an oxygen. And let's see, would this be a good problem to work through in the video? I don't think so. This one's very similar. I'll set it up for you, and perhaps it's in group 1A, so 1 valence electron, oxygen, 6A, 1, 2, 3, 4, 5, 6. I will tell you, you're going to need to double one of these, similar to how we did in these last 2 problems. And the same for this problem. There's another way I should help you on this too. Yeah, I'll tell you this. Potassium loses that 1 electron to give it a 1 positive charge. And oxygen is going to gain 2 electrons to give it a 2 negative charge. I'll stop there with helping you on that problem, because this one's better for a little bit more instructional purposes. So we have magnesium and we have nitrogen. Magnesium is in group 2A and nitrogen is in group 5A. Okay. Magnesium's in group 2A. That's 2A. And nitrogen's in group 5A. Take a sip of coffee. Good stuff. So magnesium is going to have its 2 valence electrons, 1, 2. And nitrogen's going to have its 5, 1, 2, 3, 4, 5. And this is kind of a crazy situation. Now we know that magnesium, based off where it's at in the periodic table, is going to lose 1, 2 electrons, giving it Mg2 positive charge left behind. Nitrogen is going to gain 3 electrons to give it a 3 negative charge. Now there's a few ways. We know that 1 electron from here is going to go there. And that'll give nitrogen 6 electrons. Problem is nitrogen needs 2 more. And by doing that, let's pretend that this electron can go over here. So nitrogen, by doing that, is going to have, from these 2, 1, 2, 3, 4, 5, 6, 7. Where does magnesium get more electrons? Oh, excuse me, where does nitrogen get more electrons? So we're going to need more magnesiums. So another Mg with 2 valence electrons. is going to donate to another nitrogen, or to this nitrogen. So by this one giving that nitrogen one more electron, this nitrogen has become stable. It got one electron from this magnesium atom. It got two electrons from this magnesium atom. But what about this extra electron right here? How's magnesium? Because remember, magnesium wants to get rid of two. Magnesium wants to lose 1, 2. This magnesium having that extra electron is a problem. So we're going to need another nitrogen with 1, 2, 3, 4, 5 valence electrons. And that electron is going to go over here, right there. But we have another problem. This nitrogen only has 6 valence electrons now. So how do we resolve this? We need 2 more electrons. So we're going to need another magnesium, Mg, with 2 more valence dots. And one of them is going to go right here. And one of them is going to go right here. And now we have 1, 2, 3 magnesiums that all lost those 2 electrons each. And we have 2 nitrogens, each gaining 3 electrons, giving it an outer shell of 8, making them very happy. That looks like a crazy mess, doesn't it? And it so is on this flat piece of paper that I just drew. There's an easier way to do this. If you take this number and bring it down here, and this number and bring it down here, that becomes Mg3N2. And what I have done with this is I have just represented 3 magnesium atoms, 1, 2, 3, coming together with 2 nitrogens, 1, 2, 2 nitrogens, 3 magnesiums to cancel these charges. So this crisscross method that we show in chemistry actually represents a whole bunch of stuff going on. And if you didn't get all this, which is fine on the first time, you'll get it later. We'll keep trucking on this, and it will hopefully make some sense as we try more problems. All right, with that said, let me go ahead and calcium selenide, that's CaSe, and aluminum sulfide, ALS. Aluminum is in group 3A. 1, 2, 3A. Sulfur is in group 6A. So that's V, the 1A. ALS, and I'll let you draw the dots. Ca is in group 2. Remember, group 2A, Ca. That's 1, 2. There we go. And Se is right below sulfur in group 6A. A. CaSe. I'll let you go ahead and draw those dots. I think at this point you should probably be able to come up with these charges on your own. One way that I might be able to help you on this is I will tell you that this formula is Al2S3, which means you're going to need 2 aluminums. Drawn 2 aluminums and 3 sulfurs. I'll just draw them all over the place so you can make a mess of errors like I did right there. And these 2 are much more simple and straightforward. So I'm not going to help you come up with those. You need to do these practice problems on your own. All right, moving on to naming. we have sodium, sodium, and we have iodine. When we're naming ions coming together with a metal ion that lost electrons and a non-metal ion that gained electrons, we often drop the prefix, the suffix on that and change it to IDE. So if we have sodium with one positive, like above, we have iodine, I, which iodine's in the same group number as chlorine, 7A, which means that gains a 1 negative charge. When these things come together, we call that sodium iodide. Just like up here, sodium came together with chlorine. So this is sodium and chlorine. We drop that suffix and we change it to IDE, sodium chloride, instead of sodium chlorine. Here we have aluminum, which aluminum is in group 3A. Remember that. So that's going to be Al3 positive because it loses 3 negative electrons. And bromine, Br, is right here in group 7A, which means it gains 1 negative electron. How many of these bromines with 1 negative each are you going to need to cancel Al3 positive? And the answer is right here, 3. That's going to be aluminum bromide. You do not need to stay within this box on the piece of paper. If anything, this box should have been made wider. All right, let's keep trucking. This next one is a really good practice problem for the ions. So remember that this means 3 RAs, RA, 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 and 2 nitrogens, N and N. So that means this. And how many valence electrons should we draw for all of these? Well, RA is, where's RA hiding? Radium, 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 where are you? How am I forgetting radium? RA is radium, right? I'm gonna bring up Google. Let's not go to Google. Is there something wrong with this table? Periodictable.com. Non-compliant action. Okay, Google. Periodic table. There is something wrong with our table. This should be RA, not RD. Wow, we have a wrong periodic table. All right. So anyway, back to the video. I'll have to tell my coworkers about that. Excuse me. Okay, so RA, excuse me, is going to lose 2 electrons, 1, 2, to become like radon. That's going to make each of these lose 2 electrons. So it's in group 2. So it's got the 2 dots each. And again, nitrogen is in group 5A, which means it has 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now this electron is going to go here. Now nitrogen has 6. this electron is going to go here. Now nitrogen has 7. This electron is going to go here. Now this nitrogen has 8 and its octet is complete. Now radium, is going to go there. Now this nitrogen has 6. Now this one goes there. Now that nitrogen has 7. Now that electron goes there. Now that nitrogen has 8 in its octet. So that's how those things could be conceived as bonding, which means each radon lost 2, each radium, Ra 2 positive, and nitrogen gained 3 electrons each. That's going to make it 3 negative. We would call this radium nitride. So nitrogen lost that ogen and became IDE. So now we have radium nitride. Okay. I think that's a good pausing place for the Lewis dot diagrams. I'm going to go to the transition element now. So first I'm gonna blow my nose because I'm sneezing like crazy. All right, let's get back to this. So transition metals show their charges with Roman numerals. Transition metals show their charges with Roman numerals. That's a Roman numeral, that's a Roman numeral, that's a Roman numeral. There's none there because silver, which is Ag, generally has a charge of 1 positive. So when we go to do this, we're going to write 1 positive there. We'll come back to that as we go through this. But anyway, that's a Roman numeral. Let me write the Roman numerals up here since we're doing this. I equals 1. 2 i's equal 2. 3 i's equals 3. V means 5, and the one before it means 4. So that means 4. And finally, V is 5. And notice, oh, we do have a 6 and 7. So let's go ahead and take the time to write 6. And finally, 7. So you'll notice that these also correspond to those representative group names on the periodic table: 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. So the symbol, I'll go ahead and write, let's do the first like 10 of these. So copper is Cu, iron is Fe, gold is Au, vanadium is just V, lead is Pb, that stands for plumbus in Latin, gallium is Ga, nickel is Ni, silver again is Ag. Is that 10 of them? 1, 2, 3, 4, 5, 6, 7, 8, 9. One more. Manganese Mn. So I said here, the transition metals show their charges with Roman numerals. So we have a charge of 2 positive here. We have a charge of 2 again, 2 positive. I'm going to go ahead and take the time to write another note. Metal usually form positive charges. Nonmetals usually form negative charges. Okay, knowing all that, let's keep going. Here we have gold with 3 positive. We already did silver with its 1 positive. So aluminum, zinc, and silver, their charges are up here. Vanadium, it's got V for 5. So 5 positive. This one's confusing, right? Your brain would be like vanadium, its symbol is V. What's that got to do with this V? Remember, this V refers to the charge on it, Roman numeral 5. Okay, so that's vanadium V with a charge of V, coincidentally, of 5 positive. Lead is 4, so it's 4 positive. Gallium is 1 positive. Nickel is 3. Whoa, nickel 3. Haven't seen that in a while. 3 positive. Now notice up here it's a, oh, that's zinc. Never mind, my brain's doing a little brain fart there. Silver, Ag 1 positive. And manganese 2 positive. Okay, what about the negative ions? So we have iodide, sulfide, which is going to be sulfur, chlorine, Cl, bromine, Br, nitrogen, N, sulfide, S, iodide, I, selenide, Se, sulfide, S, fluoride, F. Okay. What are the charges on these based off their positions in the periodic table? Let's go to the periodic table. Remember, iodine is here in group 7. It's going to lose, it's going to gain 1 electron. So it becomes 1 negative. Sulfur is here in group 6. It's going to gain 2 electrons, 2 negative. Chlorine is here in group 7. It's going to gain 1 electron. Bromine is here in group 7. It's going to gain 1 electron. Nitride is here in group 5. It's going to gain 1, 2, 3 electrons. Lead. Oh, no, excuse me. Sulfur that's combining with lead. It's going to gain 1, 2 electrons. Iodine is going to gain 1 electron to become electrically stable like xenon. So let's draw that 1. Selenium, Se, is going to gain 2 electrons to become electrically stable like krypton. It's going to be 2 negative. Sulfur is going to gain 2 electrons to become electrically stable like argon. And fluorine is going to become electrically stable by gaining 1 electron like neon. Okay. Now, let's just use the crisscross method to show these things coming together, as this 2 goes here, this 1 goes here. That's going to be CuI2. And what that means is 2 iodines came together to cancel the charge of a 2 positive on copper. So if you were to draw that as atoms, you would draw a copper atom, an iodine atom, and another iodine atom stuck together. So that means that. Here, the 2 would come here, and the 2 would come here, and that's going to give us Fe2S2. But because these have the same subscript, we can simplify that to FeS. So when you can simplify in chemistry, we often do. And that should make logical sense